Welcome to Hot Chips 30. Session 5. Switching Fabrics and FPGA Architectures.
Good morning. Welcome to the second day of 30th Hot Chips. It's a record year for us by all means. And we start the day with an exciting session and one of the most exciting talks. This talk the speaker will be Alexander Ishii. He's at Nvidia, but prior to being at Nvidia, he's done all kinds of exciting things in his life. He got his degree, PhD, from under Charles Lycison at MIT. And then he has been doing all kinds of hard things, starting with high-speed resonant circuits, EDA, and metro area switching, ASICs, and appliances. And now he's doing the AI appliance, right? And on the lighter side, he wanted me to let you know that he's a lot older than he looks. Okay, so no, without further ado, Alex.
All right, thank you, Pradeep. Normally these title slides don't have anything interesting on them, but in this case, there is something. Namely, you'll notice that one of our co-authors is Bill Dally, who, doesn't need a lot of introduction to this audience. Bill is the head of Nvidia research, and I think it's kind of fun to note that NVSwitch and DGX2 started as a research program originally, and I've been sort of gratified to see how quickly we're able to move it out of research and into actual product release, really, as far as I'm concerned, in a remarkably short amount of time. So what is DGX2? What is NVSwitch? Well, DGX2 is a big compute server, 10U high. It's really big. Has fancy CPUs in it, 1.5 terabytes of regular old DRAM, and 30 terabytes of NVMe storage. As far as NVIDIA is concerned, right, the heavy lifting compute-wise is by 16 of our Tesla V100 GPUs. Each one of those carries 32 gigabytes of HBM, high bandwidth memory on it. And in aggregate, those 16 GPUs buy you 125 teraflops of double precision floating point, 250 teraflops of single precision, and 2 petaflops of so-called tensor operations. Tensors are basically 16-bit floating point matrix calculations. And all told, those 32 gigabytes per GPU add up to half a terabyte of HBM2. Now, connecting those 16 GPUs together is a network that's signaling using the NVLink protocol. To build that network, we developed a new chip, not surprisingly called NVSwitch. And those switch chips implement a non-tapered fat tree, full bandwidth. And as a consequence, we have a lot of bisection bandwidth, right, 2.5 terabytes. And to me, more interestingly, the switching network, basically turns the DGX2 into a giant shared memory machine, right? Everybody's in the same address space. There are no repeaters or buffers on any of the NVLinks, and that saved us a lot of power, and in particular, PCB, more importantly, PCB area. So, and aside from just the regular speeds and feeds and results, I want to talk a little bit about, the goals of the DGX2 NVSwitch program. At the product announcement, our CEO described the DGX2 as one gigantic GPU. And I'd like to kind of go and dig down on that a little bit and sort of explain what that is and why it is we think it's important. One of the big design challenges of the box was also maintaining signal integrity in such a big appliance, and so I want to at least chat about that a little bit later on. So ignoring the gigantic part for a minute, what does one GPU look like to a programmer? Well, a programmer writes his CUDA program that sort of tells the computer what things can be run in parallel. That program then goes on to a driver process on the CPU, and that driver process can then launch parallel work to parallel copies of these GPCs, right? These graphics processing clusters shown here. Now, each one of the GPCs can basically act as, any one of the HBM memories as if it's sort of a big unified pool. And the way the different processes communicate with each other is by accessing shared data structures inside of the HBMs, right? Now, two GPUs can look a lot like one GPU, at least if they're hanging off the same CPU, right? Since it's, one CPU, you can still use a single driver process, and that process can launch work to any one of the GPCs and any one of the GPUs. That's good. The difference is that, if one GPC and one GPU wanted to talk to an HBM over another GPU, if it had to go through the PCIe bus, it hits this really skinny straw here, bandwidth-wise. And worse yet, I personally like to call the PCIe bus sort of the Wild West, right? You really never know what's going on out there. You've got, I/O to disks, I/O to NICs, whatever. And that leads to a lot of unpredictable behavior with respect to performance, right? Because you have collisions. And it's a skinny pipe, worse yet. One of the reasons that we have NVLink on our big GPUs, at least the big reason in my opinion, is that it allows us to bypass, the pitfalls of PCIe. In addition to the fact that each NVLink has more bandwidth than a PCIe bus, our big GPUs actually have multiple NVLinks. And so in addition to just being able to use a single high bandwidth path, for example, to get to HBM, the GPCs can actually spray their accesses over all the available NVLinks. And our big V100s, get up to 300 gigabytes per second of bandwidth to the remote GPUs. With that much bandwidth, two GPUs really does start to look a lot like one GPU to the programmers. So that brings us to our one gigantic GPU ideal, right? We want to take as many GPUs as we practically can and stick them all under one driver process, right? In this case, that driver process is running on a dual socket CPU cluster. And then we'd like to take all the NVLinks coming out of all the GPUs and put them in some sort of big NVLink crossbar, right, that has as much bandwidth as we can possibly provide. And if we do that, hopefully we'll get something that does look a lot like, one giant GPU to the programmer. What does that buy us? Well, one thing it buys us is problem size capacity, right? I listen to a lot of people complain about the fact that, I can't fit all my data inside of the memory available on one GPU, and so therefore I can't actually do my computation, yada, yada. Well, here, right, since every GPC can see every HBM on every other GPU, as long as you can fit your overall computation in the aggregate memory of the box, it'll go in and you can do your compute, right? So that's really excellent. In addition, as you have more GPUs, you not only add more HBM capacity, right? You have more HBM bandwidth that you can all use in parallel. And of course, you're adding a lot more GPCs, so you have a lot more compute power. So with a machine like this, there's the potential to take a problem and split it up over all the GPUs to exploit all that parallel bandwidth and all that parallel compute, and possibly get your application to actually run faster and faster as you throw more and more GPUs at it, right? Sort of classic strong scaling. And that's, one of the hallmarks of design, at least in my opinion. Last but not least, right, this machine is incredibly easy to use. Programmers that have developed their stuff on their little desktop thing with 2 GPUs or whatever, they can take that application and port it to a machine like this fairly simply, right? Because the programming model hasn't changed any from what they're used to already. And in addition, the fact that you've got so much memory and so much compute and so many GPUs makes this an incredible sandbox for people to play in, right? If you're a researcher, you just want to try something, and you don't want to spend a lot of time tuning it up to get it to fit within 1 GPU or 2 GPUs or whatever the case may be, this is your machine. The only question is, where do we get this NVLink crossbar? And the answer to that question is, of course, our new NVSwitch chip. We've got 18 NVLink ports on this baby, 1 PCIe port for management functions. And we actually fabricated this in the exact same process that we use for the V100 GPUs. Some people are going to wonder what is all this precision. And we normally quote the NVLink bandwidth at 50 gigabytes per second, which implies 25 G signaling. But I always get asked, is it really 25 or is it 25.178.125? So I thought I'd just avoid the questions and put it up there. You know, all the 100 gig Ether guys will recognize that as the sort of the standard signaling, right? And you know, and the die is not very big, right? And you can go see it outside later today if you want to. Now, the mission for NVSwitch, right, is to bridge crossbars on two different GPUs. It's not a general purpose networking device. So I'm an old network guy. You can load up a lot of stuff. None of that stuff, you know, has any place in this part. We don't have, you know, a lot of in-band signaling stuff or a lot of fancy QoS stuff because we just don't need it. Internally, though, it's pretty conventional. It's got a non-blocking crossbar, you know, data link layer and transaction layer, logic in the ports, management block, you know, et cetera, et cetera. The place where the magic happens is actually in these blocks here, where there's this, you know, this packet transforms function, right? And what's that all about is this, you know, if you remember the old diagram with two GPUs, right? NVLink was originally meant to have one GPU talk to another one, right? So if some GPU is talking over NVLink, it kind of expects the other side to respond in a way that's consistent with being another GPU. So basically, right, these transforms, they're spoofing, right? They're taking the responses from all the other GPUs and, you know, sort of reconciling them to supply one stream of responses that looks like it's coming from a single GPU, right? And that's kind of where all the magic is. As I mentioned, we use the same fabrication process as the GPUs, and as a consequence, we got to reuse the NVLink IP and reuse a lot of design infrastructure for the crossbar design, and that sped up our design time a lot. With respect to that, you know, as an example of that packet transform function, I thought I'd talk about the fact that, you know, we use physical memory addresses everywhere, right, in the machine. If you look at, you know, the old diagram with two GPUs, you know, the crossbars, the HBMs, they're all physically addressed, right, as you would expect. And since we're basically using NVLink to bridge crossbars, right, as you might expect, we use physical addresses here as well. The DGX2 and NVSwitch, they carry that model forward, right? So one of the functions of NVSwitch is that it takes the separate physical address spaces of all the remote GPUs and sort of merges them into one giant global physical address space that can be seen by, you know, GPUs that are attached to it. You know, I mentioned that NVSwitch is not a general networking device. To see that, you need only look at how we handle reliability. You know, since the switch is meant to be used inside of a single chassis, the transmission media is very reliable, right? You know, better than 10 to the minus 12, you know, generally speaking. So as a consequence, you don't need things like forward error correction, that sort of stuff, right? And that makes the design more efficient. It's good enough to just do CRC on the packets. You know, you see errors, you retransmit on a hop-by-hop basis, and that works just fine. Every now and then, something will escape those checks, so we do have internal consistency checks on the packets, right, and flag them if something looks wrong. But that happens so rarely that it's not worth having a lot of hardware to support error correction and things like our error recovery. And we basically rely on software hooks to let software come in and clean up anything that's gone wrong. We do have a couple of nice things. We have ECC on all the SRAMs, of course, but we also have it on the in-flight packets so that, you know, we can sort of cut the number of bad packets down even more. People always ask what's up with the aspect ratio of the die, and the explanation for it is actually pretty straightforward. As I mentioned, right, we're a lean and mean design, so the area for the logic is actually less than half of the area of the chip, right? Most of the, you know, 50% and plus of the area actually just goes to the I/O, right? Now, I/O is sort of the sort of thing you expect to have around the perimeter, right, of your die. And if you need a lot of perimeter for a lot of I/O, but you don't want to make the die super big for no good reason, you know, a square die is not the optimal thing, right? Something long and skinny is much better. In addition, right, by making the die this long oblong, it's possible to bring a lot of signals out in parallel, right, sort of in this quote-unquote vertical direction, you know, up and down. And that ended up making it a lot easier to route signals on the package substrate and even on the PCBs. So, you know, that's why the die looks the way it does. So how do you use NVSwitch? Well, you know, you've got 18 ports on the switch, 6 ports on the GPUs, 3 GPUs, 1 switch, and you get a little guy that looks like that, right? Why is that better than no NVSwitch? Well, with no NVSwitch, right, you would have to take the 6 links coming out of the GPUs and split them into 2 sort of subgroups, right, that we call gangs, and send one gang over to one GPU and one gang over to the other GPU. And once you've done that, right, the sort of the peak bandwidth that you can get going between a pair of GPUs is only half of what all the NVLinks could support, right? With the NVSwitch, you can get all the way up to 6 NVLinks. If you want more GPUs, you can use more switches in parallel. Here we have 8 GPUs, 3 switches. You know, here, even though it looks like we're splitting the ports up among the switches, you know, it's not the case that we're losing bandwidth, right? Because each one of the switches basically implements a plane of a network that lets, you know, each pair of links go to all 8 GPUs, right? So we really get the 300 gigabytes per second that we were looking for. Since each GPU has 6 links, sort of in the limit, it could go to 6 switches. If we happen, serendipitously, to pick 8 GPUs, we end up with a building block that looks like this, right? Where each one of the NVSwitches actually has less than half of its NVLink ports dedicated to talking to the GPUs. So what that means, right, is that in this building block, not only can the GPUs all talk to each other at, you know, a full 300 gigabytes per second, but all of them could simultaneously speak at that same bandwidth to something outside of the building block, right? So this is a completely non-blocking thing. What we do is we take 2 of these things and put them back to back, and we end up with the NVLink fabric for the DGX2, right? And this is, you know, basically a shared memory machine, right? It's all memory semantics. So you're doing load stores, atomics, whatever. Everything just works. It's really very lovely. Now, people, if they look closely, you might wonder, you know, why do you even have these switches here at all, right? Because couldn't you just take these NVLinks here and, you know, route them straight through the GPUs there? And the answer is, yes, you could. But as we'll see in a second, you know, that building block I mentioned is really a very convenient sort of form factor for, you know, manufacturing and testing, et cetera, et cetera. So we opted just to live with that extra rank of switches. So what have we wrought? Well, here are the specs. I'm not going to say them over again from the first slide. One thing I will point out is that that aggregate HBM2 bandwidth across all the GPUs, it is massive, right? 14 terabytes per second. We've thrown in a bunch of regular old infinite band NICs so we can get data on and off the machine, big CPUs, a lot of stuff. You know, all that junk, if it's running, you know, like full bore, not surprisingly burns a lot of power, right? You know, the absolute peak is something approaching 10 kilowatts. So it's a lot of juice. Big machine, really heavy. Don't try and lift it. It's all air-cooled. So, you know, 1,000 cubic feet per minute. When the thing is running full bore, it's pretty loud. Now, the NVLink fabric is dedicated to GPUs talking to each other, right? So for the GPUs to talk to things like NICs and the CPUs, we need to use a regular old conventional, albeit very large, PCIe network. But even that network, you know, we spent some time optimizing it. For example, if you take a look at how it's organized here, right, each one of the 8 available NICs basically has a clear path to a pair of GPUs, which means that we can actually RDMA from all the GPUs going to all the NICs, all at the full bandwidth supported by the NICs, and, you know, all at the same time, and move data in and out of this machine very, very quickly. You know, aside from that sort of I/O, the PCIe tree also, of course, supports the control of the GPUs and the NVSwitches themselves. Physically, that building block I mentioned, you know, 8 GPUs, 6 switches, all fits on one great big PCB, excuse me. And, you know, we call that board a GPU base board. The DGX2 has 2 of those, as you'd expect. And we connect them together with a pair of passive PCBs that we call plain cards. As passive implies, there are no buffers, no repeaters, you know, on these cards. And in fact, if you looked around everywhere on the boards, you would not find any buffers or repeaters for any of the NVLink paths. And that ended up being important, right? You know, this thing has 144 NVLinks in it, so you don't want to have to buffer all of those. And it saves a lot of PCB area. You know, the PCB is pretty packed. To get PCIe in, that whole complex plugs into a mid-plane, which is sort of really more a front plane. That's the front of the box there. And that mid-plane also provides hookup to the PCIe tree and the infinite band NICs, et cetera, as well as the CPU motherboard. That mid-plane here is also the main power distribution structure. In order to cut down on currents running through it, because they're pretty high, we ended up switching from 12-volt power distribution to 48-volt power distribution. Even at that, there's a lot of current, so we actually have copper bus bars here. That's this L-shaped structure here to get current from the power supplies up to the midpoint. Cooling-wise, we've got 4, I guess it's, 92-millimeter fans cooling each one of the GPU baseboards, and 2 similar fans that are used to cool the CPU and the various infinite band NICs and the PCIe switches. Cooling the NVMe drives here at the front of the box and the power supplies back here was sort of a challenge, and we actually ended up having to insert a couple of internal fans to help push air through those structures. Okay, so as I mentioned, maintaining signal integrity was a big problem, right? We needed to keep below bit error rates of 10 to the minus 12, a lot of links, all going very fast. And we basically had to optimize everything, right? It took forever. Even the basic structure of the network itself, originally, or at one point anyway, we were considering building blocks that actually had quads of GPUs talking to triplets of switches instead of 8 talking to 6, right? And that had a bunch of advantages, but it had the big disadvantage that we need to have these sort of long crossover paths here to get from from one triplet of switches to the other triplet of switches. And those crossover paths were just totally killing us, both with respect to signal integrity and in board area, right? Because they ate up a lot of area. So we ended up, oddly enough, deciding to make the traces going to the GPUs longer by doing, 8 to 6 type pattern, but that saved us those crossovers and totally, enabled a much more compact design. We did need custom connectors for the GPUs and for going between the PC boards, for all sorts of reasons, loss, crosstalk, you name it. And we even ended up sort of changing the standard breakouts for the connectors to improve signal integrity, grouping all the transmits together and all the receives together to cut down on crosstalk. So it works. You can keep adding in GPUs and you can get more and more bandwidth going between the 2 boards. We can get all the way up to our theoretical 1.28 terabyte per second max bisection bandwidth. This is a pairwise communication pattern, but you can also do it one to many and you get pretty much the same thing. Here, with respect to strong scaling, which I sort of harped on earlier, my personal, poster child is a fast Fourier transform. What we're doing here is we're taking a sort of a largest Fourier transform and trying to run that same calculation on many GPUs. And, this plot here shows achieved gigaflops, but as that goes up, since the calculation is the same, right, runtime goes down, right? So, here, what we're actually seeing, right, as we throw more GPUs at the problem, right, our wall time for running is dropping and dropping. So that's a classic strong scaling situation. That same, sort of test on a DGX1, which does not have the NV switches and the big NVLink network, doesn't do that kind of thing, right? What ends up happening is that the bandwidth between GPUs is, lower. So when you try and exchange the intermediate results between the GPUs, that actually ends up taking longer than just locally recalculating everything that you would have farmed off to the other GPU. So there's no particular speed up on a DGX1. The machine learning guys might be wondering, oh, do I care about this? After all, I don't do FFTs. And I claim that you do. If you take, say, a pair of DGX1s, which are each 8 GPUs, and sort of connect them together with infinite band, the amount of bandwidth available on infinite band is way less between the 2 groups of GPUs than you would get in the DGX2. And that bandwidth gap ends up buying you basically a factor of 3 in the performance of certain important communication primitives, one being this all-reduced thing that the training algorithms use a lot. And that's across the board, pretty much. But once you start going to smaller message sizes, right, like sort of like trying to strong scale in particular, you find that the NVLink network not only is higher bandwidth, but it's lower latency and other lower overheads come into play, and that 3x ends up bloating to like an 8x, right? So that's a significant thing. If you go and you cherry pick some applications where the advantages I outlined earlier can actually help you, you can actually see 2x, close to 3x speed up, right? When you compare one DGX2 to a pair of DGX1s, right? In both cases, it's 16 GPUs, so it's it's a reasonably fair comparison. Last but not least, I've been asked frequently whether people can buy NV switches, and the answer is, well, not really, but sort of. You can't buy the chips themselves, but we do have a product called the HGX2, which is essentially that building block I mentioned, right? 8 GPUs, 6 switches, all on one board. And call your vendor today, right? And with a pair of these boards, you can come up with your own solution for connecting them together, use whatever PC motherboard you want to, put it in whatever form factor you would like, and have your own sort of bespoke DGX2. And with that, I will finish with the standard gratuitous summary slide and take any questions that people have. Thank you.
Questions? David?
Good morning and great presentation. How much power does this use?
So the entire box,
the ASIC.
The ASIC. Yeah. So so I have been explicitly asked not to reveal this. As you might expect, though, since the amount of logic that we have is less than you would see in like an Ethernet switch or a PCIe switch, it actually is lower than what you would expect. I'm just doing obvious comparisons. For those that are feeling intrepid, I would be willing to reveal the fact that our PHYs are a little bit more power efficient than what you see out in the normal world. If for no other reason than we're wearing 12 nanometer, right? It's really small. But calculate it yourself from the area, right? About what the overall power dissipation is.
All right. Thanks.
Any other question? Go ahead. No? Okay. Okay, this one. So I have a question for you, Alex. So remember that one of those, I think slide 24, you show bisection bandwidth. So why does it start tapering off a little bit after 8 GPUs?
Yeah, it's not showing up there, but yes, what sharp little eyes you have. If you look at that chart, right, you'll see there's a very slight kink here, right? Mm-hmm. And the reason why that is that these are read operations, right? So in order to read data, you've actually got to send a request for that data, right? And those requests also have to go across the bisection, right, between the two boards. And so, once you go over 8 GPUs, the requests start eating into the bandwidth of the responses, right? And you get that slight tapering there. But it's very linear once you get past that.
Yeah. Thank you. Switch.
All right, thank you.
So now we have our next speaker. Next talk is Pat, are you here? Okay, so Patrick is here. Patrick has a very rich background and amazing. He's co-founder of Barefoot, and he's also from MIT, bachelor's, master's, PhD, and he did his first presentation at ISSC in 1976, and the chip had 126 transistors. And then 11 years later, he did another presentation at ISSCC with the paper that won Best Paper Award, and that had 556,000 transistors. and now he's here, and he does other, he has art, films, wines, and he would like me to note his quote of his life is he lives a quarter millimeter at a time. So.
Yeah, it kind of sounds better when Vin Diesel says, I live my life a quarter millimeter at a time. But I'd like to acknowledge that this is the work of everybody at Barefoot. It's a pretty safe bet to say that everybody there is either working on the chip, the software that runs the chip, or the software that runs on the chip. So application-specific processors have emerged in several areas over the years. First in signal processing, then in graphics. Programmable devices have displaced fixed-function devices. More recently, application-specific processors have emerged in machine learning, and now this is happening in networking too. And I'm going to be talking about a switch chip programmable in a high-level language that equals the performance and power efficiency of the leading fixed-function devices. So it's always been possible to write, process packets using software, but there's always been a penalty for doing so. Let's say on a general-purpose CPU, even with very well-optimized code, you can only get about 1/100th, something about on that order, of the performance that you can get from the leading fixed-function chip, which these days is 6.5 terabits per second of throughput for devices that are in production. Now, going to a network processor, you get at least hundreds of cores rather than handfuls. And that closes the gap, but only by about a factor of 10. FPGAs are another approach to achieving flexibility, but it's just not possible to fit on an FPGA that which you can barely fit on a really large, fully handcrafted custom chip. And interestingly, these ratios have held constant for a very long time as all solutions have gotten faster. So I'm going to start with an introduction to Tofino, our chip. And then, since some of you, I think there are a lot of people here with a CPU background, you may not have a networking background. So I'm going to go over the some basics of networking as kind of an introduction to how you do programmable switching instead of just regular switching. Then I'll get into Tofino details and then some cool things that you can do with the chip now that it's programmable. Now the questions that I want to answer today are, what is the processing paradigm for a programmable switch? And in particular, how does Tofino process packets, and how does it avoid a performance penalty? And finally, what can you do with it once you have all this programmability at your disposal? So Tofino is a switch with 6.5 terabits per second of throughput. It has 260 lanes of 25 gig SerDes, which are configurable as either 25, 50, or 100 gig Ethernet logical port configurations. It has 11 billion transistors, something under a gigabit of RAM, in a 16 nanometer technology, runs at 1250 megahertz, and is basically equivalent in area and power to the leading edge fixed function switch chips. So Tofino has 4 pipes. Processing in each pipe starts with input SerDes, receive SerDes, and then processing goes through a MAC layer, which is something that's in common that you have to do for any Ethernet connected port. Then it goes through an ingress pipeline, which is going to be the part that I'm going to kind of cover in detail. After that, it goes through what we call a traffic manager, which stores packets while they're waiting for their turn for output. And also the traffic manager's main responsibility is to choose the packets for output among all the various contending queues. Then egress processing is identical to ingress processing. Then you go through transmit MAC and transmit SerDes and out the back of the chip. So, for those of you not familiar with networking, I'm going to give a little bit of an introduction. For those of you who are familiar with it, don't worry, this will be a short excursion, and the path back will actually lead back in kind of an interesting way. So a packet consists of a series of headers followed by a payload. Each header consists of a series of words, which typically contain where you're coming from, where you're going to, and a type field, which is used to identify the field immediately following you in the packet. And this is the field that's used for parsing. Inner headers typically have many words, which are application dependent for the meaning of that particular header. For example, IPv4 has a time to live field, which is decremented on each hop through a network. So a trivially simple L2 switch would choose the output port based on the MAC destination address. And this is typically done with an associative lookup implemented by a hash table. And in hardware, that means that the match address is hashed to produce an address for a RAM. You look up the contents of the RAM. If that matches the search data you're looking for, you have a hit. Typically, there are several copies or ways of RAM, each of which have a different hash address, which then this is done to guard against hash address collisions. The hit address provides the address for an action RAM, which produces the output data, in this case, the output port. So real switches have more than one table. And in this example, again, trivially simple, the MAC table of the previous slide is followed by an IP table, or for L3 switching, you use the IP destination address to choose an output. This is a longest prefix match where LSBs and the match entries can be don't cares. So this is often done using a TCAM. And then the IP address will not only set the output port, but it may modify other fields in the packet, such as the MAC source and destination address. A third type of table is an ACL table, access control list. These match entries have multiple fields, then ternary matches are done on these. And these entries are typically filled with patterns which the switch wants to reject and drop. This is, for example, a first line of defense against DDoS attacks and other things going wrong in the switch. Now, in a real switch, these tables are much more complicated. They match on more fields, do more things, and there are more tables. And don't think a few more, think 100 more or hundreds more. And they may vary wildly in size. They may be ternary or exact match, but life is simpler in the hardware world if you think of them as just tables. And that actually kind of gives you a clue where I'm going with this, or if we're going to consider them to be just tables. So it's useful to frame our work against kind of the larger backdrop of what's been going on in networking over the past dozen years, namely software-defined networking, SDN. SDN has emphasized the separation of the switch's control plane software from the high-speed wireline processing of each packet below it. And with the result that innovation on each of these two separate layers proceeds much more quickly once they're disentangled from each other. And while most of SDN's publicity that it's garnered has been for control plane innovations, one data plane activity that I want to talk about is OpenFlow. OpenFlow was a project that worked to define in an open source piece of software the exact wireline behavior of packets as they went through a switch. So to do this, it had to start out by defining what packet header fields are. It concentrated on standard existing fields. It wanted to be relevant. It wanted to run on the switches that existed at the time. So whereas it concentrated on standard fields, we just say fields are user-defined. That makes them extensible. OpenFlow defined match tables to do ternary and exact matches. That's perfectly sufficient in general. OpenFlow defined actions as a result of these matches. But these were, again, protocol-specific. For example, you could decrement a time-to-live field, but you couldn't increment it. Some of their actions were complicated, such as do a VXLAN encapsulation. But it turns out that even complicated operations are a simple operation per header word done to many words in parallel. So we map that to a VLIW architecture with one ALU per word. And so an action consists of one VLIW instruction modifying all words in parallel. And we defined a simple instruction set for each processor. Now, OpenFlow defined processing as a sequence of match and action tables. And again, that's perfectly sufficient in general. Now, one step that we did that went beyond OpenFlow is we, together with the other members of p4.org, defined the language P4 as a language you need a language to write the code in that you're going to program the switch with. And this actually didn't exist before, which is probably my biggest surprise in getting into networking. Was there's this all of this complex behavior going on in a very large industry and no language to describe it in. So P4 has been very, very successful. P4.org has over 100 members. Basically, every company that's involved in switching as a vendor or a user is in P4. Now, the next thing that OpenFlow did is it defined an API, a software interface standard, by which it would control the switch. For example, by adding, modifying, or deleting table flow entries. But again, this was protocol specific, and so it makes it hard to extend. So Google, Barefoot, and the ONF, Open Networking Foundation, produced P4 Runtime, which is a protocol-independent API, and then that has been turned over to p4.org, which runs it now. So now let's have a quick look at P4. The vocabulary of P4 is exactly what I've been talking about, in these previous slides. MAC headers, match and action tables. So you define MAC headers, or you define headers, by just listing their constituent fields. You define tables by listing what fields they match against, and is it a ternary or exact match, by listing action functions which can be called as a result of any match or a miss, and giving the table a size. And then finally, you define table action functions, which inside them just list how each individual word is modified and how. And of course, there's more to the language than this, but this is a pretty good introduction. So P4 was designed from the start to be open source. It was designed to make switches reconfigurable with a software download instead of a silicon design cycle. It was designed from the start to be protocol independent, so that makes it extensible. It was designed to be target independent. It has been used to generate, for software implementations, to compile into FPGAs, used for NICs, used to describe the behavior of fixed function switches, and used to program programmable switches. It's vendor independent, and actually there was a tutorial on P4 at last year's Hot Chips. P4 Runtime is also, as I said, open source and run, essentially the property of p4.org. So now I want to get into Tofino hardware. Processing starts by parsing packets. Now, the individual, the packet header fields that are defined by P4, each header forms a node in a parse graph with edges to any other header field which can immediately follow it in the packet. And the sequence of headers of an individual packet represents a path through this parse graph. If you consider the nodes in this parse graph to be states in a state machine, the state machine walks this parse graph. And the state machine is implemented using a TCAM, which matches against current state and the set of input fields to match on. And it produces the next state, the next set of fields to match on, and commands to extract words from this individual header into a structure which we call a packet header vector. And this is actually just a set of registers, thousands of bits wide. At the end of parsing, this is populated with all of the headers in positions that have meaning to the compiler, but no meaning to the hardware. These words come in 8, 16, and 32-bit sizes, but other than that, they're all treated identically by the hardware. So when parsing is finished, the individual packet header vector is muxed together with the results of all 16 parsers that feed a pipe, and it's ready for match action processing. Now, the block diagram of this match action unit is going to look suspiciously similar to some of the diagrams I've showed earlier, showing how match action processing works, because it just directly implements those block diagrams. Packets come in, they get registered, they go through a crossbar which extracts fields for matching, and those go to either SRAMs for exact matching or TCAMs for ternary matching. For exact matching, a hash generator generates the hash addresses for the RAMs. The output of a match is an address which drives an action RAM. This output data produces an address for an instruction RAM and operand data. So now instructions and data drive each individual word of the VLIW action engine. All of this is a feed-forward pipeline with a throughput of 1 packet per clock cycle, and it's stateless. Once a packet has gone through, there is no state that has been altered by its traversal, so there's no memory of its traversal that remains in the system, which actually makes verification a much simpler simpler task. Now there are portions of the portions of the MAU match action unit which are stateful, and these are functions which are common to any switch. For example, statistics. You may want to record, and this is a common function, the number of bytes or the number of packets that have matched at a particular flow entry. Well, that increments a memory which is taken from the pool of RAMs, and that's by definition stateful. So meters and statistics are in this category. We also provide a general purpose stateful ALU, which is user programmable, that again takes RAM from the pool of RAMs to record its state. And this turns out to be, this will be very useful, and I'll may mention this in some of the applications later, but that's a very useful addition to the processing. So P4 defined tables, and it defined, I didn't get into it, but it defines the sequence of table execution. And this can be used to build a table graph. It's really, the parse graph and the table graph are really the two internal representations that you can think of to model how these things work. And multiple small tables fit in a single match action stage. Large tables can spread across multiple stages to gather the RAM resources they need to implement a table of their required size. So the match action pipeline, that ingress pipeline of the block diagram, is just a sequence of identical match action stages. Now, table predication is what allows multiple tables to run concurrently in a single MAU stage. So if you take the table graph on the left and rearrange it into a linear sequence, what it starts to look like is either the fall through of instructions in kind of linear execution or short forward branches. And what happens with a short forward branch is you just invalidate, predicate off any table that was skipped. And this happens in the middle of the pipeline, essentially after match and before action. And it turns out that it takes one AOI21 fan out of 2, I believe, gate to do each level of this. So you can actually put quite a number of tables in an individual stage before this would start to become a timing problem. So now, as we've seen before on the last slide, multiple tables can fit in a single stage. And those control dependencies, next table dependencies, don't force tables to be put into separate stages. But data dependencies do. For example, if the IPv4 table near the bottom produces a result, which modifies a field in the packet header vector, that the next table, the ACL table, is going to use to match on, the ACL table can't even start until the match table, until the IPv4 table is finished. So those two stages must run sequentially, but multiple stages with no data dependencies run concurrently. So how did we get the programmability without the penalty? Well, the first thing is we didn't try and just force everything into a computer model. And to be fair to network processors, they can do a vastly different set of tasks, but we didn't try and use that model. We took the existing pipelines and made them configurable and programmable in just kind of the minimal way. This is a very regular architecture, and the regular architecture affords you the opportunity to essentially work harder on each individual block and produce a better design as a result. Finally, if you look at the MAU area, you can roughly divide this into two categories. And the first category, by far the larger, is dominated by stuff like RAM, which you have to have in any switch. And there's a lot of it. There are hundreds of megabits of match tables, and this is kind of a primary care about. And RAM has support logic like ECC and functions attached to it, and there are standard switch features. Well, if you take this, subtract all this out, and can call everything that's left over the programmable part, well, that's about 10% of the chip area. So if this cost nothing in a fixed function switch, we would be at a 10% penalty. But these are functions which have to occur in a fixed function switch also. You need to modify packets, you need to extract packet data to match, and probably more importantly, you need to transfer all of these bits which are going to be matched on or modified, get them to all the RAMs and the units which are going to modify them. And because this is a lot of RAM, this covers some distance. So the area is really kind of down to a wash. Now, we did get a benchmark in terms of power. It turns out there's an OEM that produces 2 switch boxes, both 6.5 terabits, one with our part, one with the competitor's part, and they list our part as having lower power. Now, we could quibble about, well, is that big? Is it different? Is it that important? But the important point is that the programmable part did not cost more power, which is what everybody would have expected years ago. So, switch performance is a very different animal than CPU performance. CPU, more is always better. And that's also true with network processors. Network processor performance is kind of a squishy affair. It depends on what application you're doing as the throughput that you're going to get. Hardware switch performance is deterministic. You have to accept 100% input traffic on all your input ports. End of story. It's very simple. Turns out most important switch parameters tend to be things like RAM sizes. How much data RAM do you have? How long can you in-queue packets before you have to start dropping them? How big are your table sizes? And finally, there are a lot of behaviors required before you can call yourself a switch, most of which are related to the traffic manager and algorithms for selecting packets for outputs. So now I want to talk about applications. What can you do with a programmable chip? And these fall into 2 categories. And the first one is just things that make switching better. And the first one is kind of the most obvious one. You can scale the table features that you want, larger than the table features that you don't want so much of. And actually, the most important scale factor is 0. Just get rid of features that you don't want. One OEM told us that they have a lot of security holes, which they work very hard on, related to switch features, that come in chips, the features that they don't use. So the first thing they do is get rid of these features and sleep better at night. And then that gives them more space to scale up features that they do want. Now, the first killer app of programmable switches is in-band network telemetry, INT. And the way this works is that on each hop through a network, data is added to the packet saying, well, for example, what switch it went through and when and how long it was at that switch. Now, this information is extracted at the network edges and compiled from all locations. And now you can answer the question: if I got delayed in a switch, who delayed me? And so even if you have microbursts, congestion events that last microseconds, you can find them where this has not been possible before. Actually, the CTO of AT&T described the visibility this gives them into their network as the difference between having X-rays and going to MRI. It's actually that significant. Bloom filters are actually a neat little primitive that allow a membership test. And these are implemented using stateful memories, the stateful ALUs, and form components in some of the applications below. Counting Bloom filters allow you to do, say, how many times I've seen this flow before. And this can be used for what they call heavy hitter detection, finding flows that are hogging bandwidth. Now, the other type of application is really brand new, and we call it computational networking. And this is taking functions which used to require a CPU and doing them to the packets as they traverse the switch. And when you do this, you automatically get hundreds of times the throughput at hundreds of times less latency. A first good example of this was Layer 4 load balancer, which is in last year's SIGCOMM, a very nice paper. Turns out Layer 4 load balancing is actually a complicated problem. When you make a request of Google send a request into Google, the first thing that it does is has to fan out everybody's requests to all the servers that are going to handle them. And this is hard for 2 reasons. One is you have to stay with that server through the duration of your session, even though servers go up and down all the time, which normally would change the distribution algorithm. And second, there are millions of these connections which have to be remembered. And this is complicated enough that it's been done before. It's done with CPUs, and it typically requires 3 to 5% of all the CPUs in the data center to handle this. And now you can replace something on the order of 500 CPUs with one switch. So this is an example of something where, as the packets are going through the switch, it's in the perfect location to provide some extra processing and actually have a transformative effect on an application. A DNS cache is the same category. These requests normally get fanned out. If you cache the frequently used instances, it's good for load balancing. It's good for prevention against DDoS attacks because you can't overwhelm it. The same thing is true in a data center. The data is stored in disks, typically accessed through memcached, but what you actually sometimes need is a much faster cache in front of that to handle cases where an individual piece of data gets just many more requests to it than it can handle. So once again, the switch is in the perfect location. So I guess I could say, as in networking, as in real estate, it's location, location, location. And finally, for those of you who are at the machine learning tutorial on Sunday, if you use a data parallel model, there are lots of servers, each of which are kind of fanning out as subsets of the data. On each round of forward and back propagation, parameter updates from all these servers have to be summed. And this is either a multicast, everybody's data to everybody else, and that n-squared traffic doesn't scale very well, or all these parameters are transmitted up to a parameter server, which sums them and then sends them back. But again, this is a CPU, which introduces a lot more delay and a lot more latency, and this can be done in the switch instead with much improved performance. So in summary, we believe that switching is going programmable, and Tofino has demonstrated that this can be done without a performance or power penalty. P4 lets people write programs to make the switches do what they want to do, and now they have something to run it on. And we believe that this opens up the domain of wire speed processing to the computer networking industry, which will lead to very interesting and exciting times over the next several years as innovation is unleashed. So, thank you.
Thank you. So we ran a little bit over, so we have just time for a couple of questions.
Excellent talk. Just one quick question. How much of that programmability that you talked about, at least within the data center, could be done by a smart NIC? And how much of it can and will be done on a switch like this?
There are all sorts of people have different opinions on this. There's some people think that you can do encapsulation and decapsulation in the NIC, and then the network can be dumb. There are other people that believe opposite, and actually everybody's doing things different ways. So this is an experiment which has been ongoing for many years and will probably continue on. On the other hand, things like INT have to be done in the switch. So you need that intelligence in the switch. Once you get into the network, the network is not this perfect thing that lets you instantly get packets, put packets in one end and get packets out the other. It can have hundreds of thousands of nodes and very complicated internal behavior. So we believe that intelligence is going to be required in the switch.
Okay. One more.
Jeff Smith from Citadel. Is this switch a cut-through design or store and forward?
It will do both, either.
So if it's in cut-through mode, what incremental latency do you pay for different DAG path lengths for more rules, I guess?
The DAG path length is set up at compile time, and so all packets have the same latency through. So
the most complicated rule determines the latency through the switch wire to wire?
Yeah, essentially the table graph determines the latency. And of course, things will vary by a few hundred nanoseconds from best case to worst case. It's not that much.
But the uniform length makes sure that if you have different rules, like an application layer, that you don't have to worry about reordering packets on a given flow.
That's correct.
Okay.
Yeah, when you set up a pipeline, every packet has the same latency through the pipeline. Whatever path it goes through, whatever path it goes through the table graph.
Okay, thank you very much. Great talk.
Okay, so in the last 10 seconds, I can sneak in my questions. So
Yeah.
you said regularity in the architecture helps design. So can you quantify it or give some examples?
Yeah, actually, as it turns out, I guess I'm kind of an old school designer. I like doing things custom, and the regularity afforded me the chance to do this. We have hundreds of millions of gates on this chip, which, of course, you design it behaviorally, but the real implementation is designed at the gate level. All the gates are fixed placed. All the important wires, all the long wires are pre-routed to the point where this is a fully custom design. For example, the data path in the VLIW ALUs, instruction decode is synthesized, but the actual data path is hardwired. So this dominates our performance, and it gives us, I believe, big improvements in both performance and density.
Okay, thank you. So our next and last speaker for the session is Juanjo, and he's Juanjo Noguera. He also got his PhD from, he got his PhD not from MIT, but from UPC in Barcelona. And prior to moving to he's currently director in the architecture group, and prior to this, he was in the CTO office at Xilinx, and he also worked at Hewlett-Packard in Barcelona, right? So now, Juanjo.
Thanks. Pleasure to be here. So back in March, Xilinx announced Everest. Everest is the Xilinx next generation architecture. And within Everest, one of the key building blocks is this hardware-software programmable engine, which so far Xilinx has not given too much information about. This is the first time that we're going to provide a bit more details about the contents of this hardware-software programmable engine. This block started in the architecture of this block started in the CTO office quite a few years ago, but has been in product development for quite a few years now. As you can see from all the people listed here and many more that are missing. The thing I would like to emphasize is this block, this hardware-software programmable engine, has been co-designed and taking into account all the inputs from all the different groups, from applications, compiler, architecture, and silicon implementation. So this is an architecture talk. I'm going to give you a bit, as I said, one level down detail into the contents on the architecture of this block. I'm not going to talk about the Xilinx next generation product. For this, you would have to wait a bit of time. And let me just jump into a bit more details of this talk. So this slide just tries to capture what Xilinx announced back in March. As I said, Everest is the next generation architecture. It's a heterogeneous architecture built of processing subsystem, programmable logic, programmable I/O, and then there is this hardware-software programmable engine. In the rest of the presentation, just for simplicity, I'm going to call it a software programmable engine, and I'm going to slowly go and walk you through the key innovations in this block. This block provides compute efficiency. It's a massive boost in the compute capacity of the architecture, reduces power, and it's software programmable. On the right-hand side of this slide, what you can see is a few benchmarks that Xilinx has also announced in March. There are two main benchmarks for which we have designed this architecture. This is for machine learning inference and 5G wireless. And you can see, compared to existing Xilinx products, what's the performance boost and the application-level performance that you get by using this software programmable engine. Also has been made public that this block, this Everest architecture, will be taped out this year, and it's the first architecture that includes this hardware-software programmable engine. So let me dive a bit more into go one level down. No? You have probably seen these simplistic pictures. This is maybe also a bit high level still, but maybe a little bit more detail. What you see on the left is the processing subsystem with the application processors, the real-time processors. You can see the programmable logic with your lookup tables, DSPs, embedded memories, VRAM, URAMs, and then you have your programmable I/O, where you have this transceiver, PCIe, DDR, HBM, And integrated, if you are following Xilinx, you have seen recently the announcement of integrated AMS, analog and mixed signal, with integrated DACs and ADCs. So what you can see in red in this picture is this software programmable engine. It's not a monolithic block. It's scalable. It integrates multiple programmable engines. In this picture, we are showing 6, but it's just an example in this slide. There are many more, and I'll go and explain more later in the following slides. And then you can see it's a domain-specific architecture. It's targeted for, as I said before, machine learning inference and 5G wireless. It's hardened in 7-nanometer technology, and it's a throughput-oriented and low-latency architecture. You can see it talks, if you look at how the interfaces of this block, you can see on the left, it talks to the programmable or the processing subsystem. That's basically the processing system just controls it's for software control, boot, configuration, error management, more details later on. And then it talks to the programmable logic fabric for the high bandwidth and connectivity. Get all the data that you need to provide to these compute engines so you can feed the beast. In the programmable logic, it's soft logic. It has a lot of flexibility, not that in this programmable engine. As I said, this programmable engine is tuned for machine learning inference, 5G wireless, and the FPGA fabric next door can do a lot of many other applications, and we'll explain this later. So it has a lot of flexibility. And we think the combination of the two is the one that gives a unique differentiator for Xilinx. For example, you can implement your own custom memory hierarchy in the programmable logic. Different architectures or different products, different chips from this architecture will be announced shortly. And again, for this, you'll have to wait for a couple of more additional months. Now, let me just show you a couple of drivers of why we developed this architecture. So one is for data center, machine learning inference. You can see there is a massive increase in compute due to all these machine learning inference requirements, and you also can see there is upcoming requirements for lower latency. And the other one is, I don't need to talk more about this, I'm sure everybody knows. The other one is that there is heterogeneous workloads in the data center. You can see there is video, genomics, financial, database acceleration, networking, storage. There is a lot of different workloads. And all of them we can observe there is a trend where machine learning is becoming an essential part of the data processing. So how would we take this and map this on the architecture, on this Everest architecture? What you can see is we can map all the high compute, intensive, massive compute on the software programmable engine. You can map your convolutions. You can map your fully connected layers. You can map your the pooling layers or the activations. You have the compute power and low latency of the programmable engine. And then in the programmable logic, you can implement your custom memory hierarchy. The memory hierarchy is where we want to go for low byte sizes, where we can stay on chip, reduce the power, so we don't have to go off chip, and we can have low latency, as I said before. And in addition of that, we can put all these in the programmable logic. We can put the additional workloads. We can put the video, genomics, finance, database acceleration workloads. Now, moving on, the other second driver is this wireless 5G. I don't want to spend too much time on this slide. I'm running behind, so I'm just going to say that there is a data increase in data and traffic capacity, more increased data rates, and lower latency. And on top of that, there is new technologies. There is massive MIMO. There is there is a lot of flexibility because multiple antenna configurations, different frequency bands, and on top of that, the traditional partitioning of the functionality, it's also changing. And what you can see here in this slide is probably a bit of a traditional pipeline of what will be implemented in a wireless base station, in the wireless infrastructure. That's what this chip is designed for. So if we want to implement this on the programmable engine, that's what you would, and we just take as one example, what would be the digital radio with integrated DACs and ADCs how do you split the functionality? How do you implement this on the Everest architecture? You would go and you put the compute on the software programmable engine. You could put the IOs on the programmable logic and the integrated AMS, and you can put the control on the processor subsystem. Now that I've given you a bit of a motivation of why we are doing this architecture, let me jump and dive into a bit more what it is. So, as I said before, and that's what the picture on the left, in the top left tries to say, it's a modular architecture. We're building one tile as the building element. This is the element that we're going to optimize, and the design team is optimizing to reduce power and reduce area. What you can see in this tile is three parts. One is a processor, is a vector processor, is a VLIW vector processor. And just to give you an order of magnitude, we are talking of hundreds. I'm not going to give you the details of how many the throughput, but it's hundreds of operations per second. In addition to the processor, there is the local memory, and there is the interconnect. The interconnect can talk in all the different four cardinal directions, and the processor can access directly memory from its neighbors through this red connectivity. As you can see, this processor has a specialized instruction set or has vector extensions for machine learning and for wireless 5G. We have optimized the instruction set for this type of applications. The next one is the local memory. The local memory is a multi-bank implementation and is shared, as I said before, across neighboring cores. So neighboring cores can directly access the local memories. Moving on, there is the interconnect. This is an interconnect which is non-blocking. It provides point-to-point connectivity between different tiles. In each of these arrows, it's shown as just one interface, but there are multiple interfaces in each of these links, and it can provide an aggregated bandwidth of more than 200 gigabytes per second per tile. Integrated into the data memory, there is a data mover. That's basically to help us in the process of doing compute and communication in parallel. So while the processor is computing, we can move the data through a DMA. This can be used to interface to non-neighbor cores, so non-neighbor data communication, and it has integrated synchronization primitives. And finally, you can see this green arrow is what we call a cascade interface, which it can be used to send the partial results to the next core, to the neighboring core. It's a direct point-to-point connection as well. As you can see, this is a tile, but it has leveraged a lot of traditional functionality that you can find in Xilinx products today. The cascade is very common in Xilinx products. The interconnect, it leverages the spirit of the Xilinx routing resources. Instead of being at the bit level, it's at the word level to have more silicon efficiency. Now, moving on, we have optimized this building block. Now we need to to create this programmable engine, we instantiate multiple of those. And as you can see, we just take the tile that we have optimized and create multiple instances. There is an architectural focus in the architecture to have deterministic performance and low latency. As you can see, there is no caches in this architecture. The interconnect is deterministic, it's point-to-point. And all this is to guarantee performance and have deterministic performance. And I said low latency. So as you can see from this picture, again, this picture is just one example. This is a massive multi-core array of engines to increase the compute. It's a modular and a scalable architecture. You can instantiate multiple tiles to get more compute. The memory scales, obviously, with the compute. And just to give you an order of magnitude, we are talking tens to hundreds of these tiles instantiated in the product. And as I said before, there's going to be different products, and each different product will have a different combination and numbers of these engines instantiated. It's device specific. And then, as I said before, this is distributed memory hierarchy. Now that I've shown you a bit how, given a bit more one level down what is this software programmable engine, let me explain how the data would move in this architecture. The first one is the data movement architecture. I have two slides. This is the first example. Is use a very simple data flow pipeline where you have one engine sending data to the next engine through the shared memory. As I said before, the one processor can talk to the neighbor through this shared memory, so there is no interconnect involved. And one topic that is, or one theme that we use a lot in that architecture is this overlap of compute and communication. And in this case, you build a traditional pipeline, super simple. This is the basic way of communicating. And you can obviously create multiple instances of this pipeline, maybe of this data flow pipeline. Another example would be this data flow graph, where you have one engine. Again, it can talk through the shared memory to its neighbors, and then you can have multiple pipelines working in parallel. And in the end, you can combine them and produce one output. So basically, you can build graphs out of this architecture, this data flow architecture, and you can build data flow graphs. And the other one, a third example is this, what we call streaming multicast. So you can, through this, in this case, you have using the interconnect that I was explaining before, you can send the same data to multiple engines. This is extremely useful in machine learning, as probably all of you know, and also it's useful in many wireless applications. Maybe a couple of more. In this previous example, I've just shown you what would be neighbor communication. In this example, I want to talk to a remote tile. So you can have this topology where you have two tiles talking through the interconnect in the middle, in the blue. And just to show you how this would be implemented in reality, just as an example, you have one engine, this processing engine 0, on the bottom left. And then through the shared memory goes the data mover, takes the data, puts it through the interconnect, and it reaches the second engine on the right, on the top right-hand side. Again, this is fixed point-to-point connectivity, and we have the two engines working in parallel through having small buffers being transferred through the interconnect. It's buffer to buffer through the interconnect. And the final example I wanted just to mention is the cascade interface. No? In this example, we have two engines, both connected through this cascade interface. Imagine that the architecture can build a dot product, but let's say for whatever reason you want to build a bigger dot product. So you basically can cascade two of these engines through this interconnect, and you send the partial results from one engine to another. Or if this is the machine learning case, where you need to do dot products, and you can build a bigger processor. The other option is you go and you build, for example, in wireless, you need to build a filter. You have a sample rate, 1 gigasample, for example, sample rate. What you would do, the one processor cannot sustain that compute. So what you do is you split the coefficients of this filter into two engines, and that will help you in sustaining the sample rate. And again, how this will be mapped on the architecture. In this example, these two engines are mapped, and as I said before, there is a point-to-point between processor 2 and 3. There is a point-to-point connectivity. In this case, the data comes through the stream and directly goes to the core, so the core has instructions to read and write from the streams, and there is no local memory being used in this example. One more is about, just to finish on the architecture section. This is about the device integration. So we have this massive array of engines. How do we integrate with the programmable logic? So basically, we have a simple interface inside this array that enables us to connect to the fabric. We have simple clock domain crossing to connect the programmable logic to the engines. This clock domain crossing, there is some small FIFOs in there. And that's simple. And then just to give you an order of magnitude, how much bandwidth do we have in this interface? We're talking of up to terabytes of bandwidth between the programmable logic and this array of engines. You have a lot of compute. You need to make sure that you can provide all the data for these engines to do the compute. And that's how we achieve this result. And now, how can this be used? What kind of examples of what can I build? In this example, you have the software, 2 cores that need to, in this example, these 2 engines need to interface through a bigger shared memory. We can implement this shared memory inside the programmable logic using URAMs or VRAMs, the programmable logic resources in the fabric. This is a way to achieve stay on chip. And as I said before, we can use it for low batch size. We want to achieve low frequency, so low latency. We want to stay with low batch size, stay on chip, and don't go off to the reduced power. And then another example of this use is we can have a programmable accelerator. We can have, in the fabric, we can have an accelerator to help these engines. We don't need to have an instruction set that covers all the possible applications. We have FPGA next door, and that's where we can implement the specialized functions to help in this engine. And you can do pre and post processing, and you can do also co-processing. But anyway, I'm sure that's, and we use that, for example. You could use this to create, if somebody comes with a new layer in machine learning, we can implement this new layer. It's not efficiently mapped onto the programmable engine. We can put in the programmable logic. Now let me talk about the programming environment. So the first thing is, in this slide that I would like to emphasize is that there is going to be a device-level programming for Everest. There is going to be high-level programming languages, like, for example, C and C++, that will go into the device compiler, and this will call under the hood the different fabric compilers. So there will be a compiler, obviously, for the processor subsystem, for the software programmable engine, and for the programmable logic. And if we just take, as one example, we just take this simple wireless radio that I mentioned earlier, where you have a pipeline of kernels. This is just one example. You can describe this graph and this connectivity through C and C++. Each of these engines will go and be implemented in C, will go through the compiler for the core. That's, as I said before, a VLIW compiler. And then and I'll have more slides in the later slide. And then it will also do the partitioning into what goes into the programmable engine, what goes into the programmable logic. This will not be, this partitioning will not be done automatically by the compiler. It will be done will be guided by the user. Now, going back a bit, or going one level down into this software programmable engine, and what are the key software, all the building blocks in this software stack. The first is there's going to be there is a full software programming toolchain. Includes your preferred IDE. There is a compiler. The compiler, obviously, there is a compiler for the core, for the VLIW compiler, and there is a compiler for the whole array. So the user doesn't need to know about the DMAs. The user doesn't know about the streaming interconnect, how to do the routing, and so on. That's hidden from the user. There is obviously a debugger. There is, in the architecture, there is multiple features to support the debugger, not only at the single core, but debugging at multiple core. And there is this performance analysis. Obviously, the architecture don't have time today to go through all of this, but includes all these. There is performance counters, there is tracing capabilities, and all this will be exposed to the user through this performance analysis tool. In addition to the software toolchain, there is going to be optimized libraries. There's going to be 5G libraries, machine learning libraries, vision libraries, and so on. And then there is also the runtime software. The runtime software will run on the PS, will be do for error management, memory management, boot configuration, power, thermals. These are just examples of the type of complete functionality that we need for the runtime software for this programmable engine. Let me speed up a bit here. I'm running a bit out of time. For the machine learning, so there is going to be, Xilinx has an existing compiler, machine learning compiler that can take from any framework and implement that functionality on 16-nanometer products. This compiler is extended to support Everest with math engines, with the programmable engine. And then there is, the user will keep working at the programmable, at the framework level. The user will not see the user will not see the programmable engine, and it's going to be a seamless migration. So the existing models that you have working on 16-nanometer products will be migrated to this architecture. In terms of application results, just a couple of high-level messages. This slide is just trying to show for kernel-level performance for a few benchmarks for machine learning and wireless 5G. The first one on the left is the convolutions. It's a matrix block-based matrix multiplication. FFTs and DPDs is just a nonlinear filter that you need for wireless communications. The point of this slide is at the kernel level, we achieve high compute efficiency for all this key functionality. Now, just to take this one level up, what does it mean? I've shown this big jump in performance from 16 to 7, enabled by this block. I've shown this at the beginning. Let me just explain one level down what this, for machine learning inference, this is basically the image classification. This is a Google Net running on the UltraScale Plus products. This is public information. You can find that. And then this is the performance that we are anticipating for the Everest architecture. So there is going to be an order of magnitude increase in the application level performance. An order of magnitude. In addition to that, you're going to achieve sub-millisecond latencies. Okay? Sub-1 millisecond latency. So we're talking hundreds of microseconds of latency for this type of computes. On the 5G's wireless, this example is a massive MIMO radio with all the filters. And again, there is quite a bit of jump. And just to give you an order of magnitude, what can you achieve? You can achieve up to 2 gigasamples of sample rate. And for the ones of you what this means, this is a lot of compute. Up to 2 gigasamples of compute for wireless 5G. And on top of that, there is the 40% reduction in power. Let me just wrap up. Today, I've shown you this new block, giving you more details. It's a domain-specific architecture for machine learning inference and wireless 5G. Increasing compute is going to be hardened. It's taped out this year in 7 nanometer as part of the Everest architecture. Everest is a heterogeneous architecture. It includes the high compute of this software programmable engine integrated with the flexibility of the traditional FPGA fabric. It's being targeted for multiple applications today, and I've shown you as the 2 key drivers, machine learning inference and 5G wireless, but there is also in automotive and in cable access. This architecture hopefully will be used. And the last bullet I would like to emphasize is that this is going to be obviously software programmable. There is no synthesis, no place and route, no time enclosure. This is just all programmable from C. So you have your compile, execute, and debug with optimized libraries. If you want more details, Victor will give a keynote later today, and there is going to be the Xilinx Development Forum in October. That's where there will be more details about the architecture and Xilinx-specific products. Thanks for your time.
Thank you. Time for a few questions.
Yes, John Lockwood of AgroLogic. So fascinating to have the coarse grain mixed with the fine grain. It really enables a lot of features. What kind of frequency are you targeting for the coarse grain blocks?
So today I cannot disclose that information. I sort of indirectly try to hint to this when I mentioned the 2 gigasamples. It's going to be in the order of gigas. I cannot give you the exact number. I'm not allowed to disclose the number of engines, the compute per core, power, area, frequency. Apologies, I was running out of time. I couldn't mention this earlier.
What about word size? I mean, it's VLIW, so it can be wide, but in terms of like targeting the C, C++ compiler, what kind of, would it be 64-bit, 32-bit, mostly?
I cannot disclose this today.
Thanks.
Thanks.
Hi, thanks for a great talk. I'm Shrikant from Google. So the question I had to do has to do with the programming model. Seems like you have high-level programs in C, C++. So do they have to be aware of the architecture? In other words, you seem to be splitting a single thread of C++ into these multiple computation engines. So is there anything to sort of inherently synchronize and make it equivalent to the single-threaded C++ code?
Well, as I said, I mentioned this, inside the architecture, there's obviously synchronization primitives that will help us in synchronize this, if you build these pipelines. This is not a traditional, let's say, multi-core architecture. It's a multi-core, but with a lot of features leveraged from the traditional FPGA architecture, where you have, again, pipelines, you have dedicated, this node share interconnect, is point-to-point, no caches. So all this basically enables us to have, this kind of level of RAM. And the one model, just to be clear, is what I said, this pipeline of kernels with a data flow type of programming model.
Yeah, one quick follow-up. So what breaks up your application program into that structure that you described? Is there like some tooling to do that, or?
Sorry, I didn't understand the question.
So there is the user-level program, right? And then it gets broken up into these processing elements. So where does that step happen? Is it the user who's supposed to do this, or?
So short answer is yes. More details of the programming model will come up. But short answer is yes.
OK, thanks.
Hi. Very impressive. Look forward to using it. So first question was just in terms of the PE, is it basically a fixed point architecture, or is there any capability on the floating point side?
It supports floating point as well, yes. And I didn't mention this in the fixed point, obviously, because we're doing wireless, there is complex arithmetic in support. And then there is multiple precisions in the support. It's all your favorite machine learning precisions will be supported as well.
Okay, good. And second question, similar to the first one, really. In building compilers for these FPGAs and architectures like this, what always jumps out at you as fundamentally obvious in this heterogeneous world is you need to get your data flow planning at the front end before you get to your C to gates. And so my question is, does your tool flow have some very nice, user-friendly data flow planning in that tool flow?
As I mentioned earlier, I'll answer this question a bit. There is a data flow, and this graph with the data, as one example, can be expressed from C, C++. Hope that answers your question. Thanks very much.
Hello, Jan Gray, Gray Research. Similar questions. So in the processor, you mentioned it's a vector processor. Does the programmer, is it an auto-vectorizing compiler you have? Does the programmer write intrinsics? How do they get their vector intent expressed in your instructions? And then secondly, for the data flow, do you use explicit message passing? Do you use pipes, OpenCL pipes, or what is the programming model there? Thank you.
So maybe on the core side, there is no vectorizing compiler. So that hopefully answers the first question. We're doing different things to help on that front. That's not easy, so we understand. And the second one, there is at the current model. I wouldn't go through all these examples that you have given. It's much simpler. Again, think of it as one example, just to let me reemphasize. One example is just this pipeline of engines connected. And
in my code, I say get the data. So do I suck on a pipe, or does it magically populate? That's the kind of.
Maybe we can take this off during the break, if you don't mind.
Thank you very much. Thank you.
Okay.
Thanks very much.
Thank you.